Welcome everyone. My name is Andre Kohn, and in this video I want to introduce you to the problem of monolithic aggregation operators in today's database systems, and how our paper, Building Advanced Analytics from Low-Level Plan Operators, is solving it. This paper was joint work with Victor Leis and Thomas Neumann. Let's start with the first simple SQL query. This query joins the three relations R, S, and T using the two predicates A equals D and C equals E. Most relational database systems today will translate this query into a tree-shaped relational algebra plan which could look like the tree shown on top. Here it consists of 6 operators, 3 table scans, 2 joins, and a topmost projection. The pseudocode on the right shows a simplified program that could have been generated for such a query. The different colors indicate which operators are responsible for which line in the code. The plan here first scans relation R and inserts every row into a hash table of the blue join. It then scans relation S, probes the hash table of the blue join, and inserts every match into a hash table for the orange join. Afterwards, it scans relation T, probes this last hash table, and projects the result tuples. As you can see, the complexity of this program is spread out evenly across the different operators. Let's take a look at another example query. This query only scans relation R and computes the 3 aggregates median, average, and a sum with distinct qualifier. The corresponding relational algebra plan is much simpler than before and consists of only 3 operators, a table scan, a group by operator, and a topmost projection. If we take a look at the pseudocode, however, it is now significantly more complex and is primarily generated by the single group by operator in the mid. In this paper, we argue that such monolithic aggregation operators are common in relational algebra and that they are the result of the set semantics that do not allow us to break up aggregates at the plan level. If we take a closer look at the aggregates, we can see that they are actually very different. First, there's the median aggregate that requires its input to be materialized and at least partially sorted by A. Then there is the average aggregate, which is decomposed into the aggregation functions count and sum and does not require the input to be sorted. And then there is the sum with distinct qualifier, which requires all C's to be unique within every group D. A common way to make these values distinct is a preceding hash aggregation. Here we use the pseudo-aggregation function any, which selects an arbitrary element per group. We then aggregate C and D by key DC first and re-aggregate these values by D for the sum. In the end, however, the user still wants to see all these aggregates at once, so we eventually also have to join those aggregates by group key D again. We argue that such composed aggregates are just too much of a burden for a single operator and inevitably lead to many handcrafted optimizations that are hidden from the rest of the plan optimizer. For instance, the median computation in our example will require a partition-aware sort implementation. The database very likely already has a sort implementation for general order by clauses, but since that operator conceptually produces a set of tuples, we cannot simply reuse the operator for the median computation if our engine does not explicitly materialize all intermediate results. We therefore propose to split these operators into so-called low-level plan operators that modularize the aggregation logic and lift the optimization of complex aggregates to the topmost plan level. More precisely, we propose to extend the traditional relational algebra plans with the concept of physical result properties. These physical properties specify whether an operator result is materialized or not, and whether it is partitioned or sorted. With these few properties, we can split group by operators just enough into 8 slightly smaller building blocks that still preserve the flexibility of logical relational algebra operators, but can be optimized and composed in a more streamlined way. These low-level plan operators are shown in the table on the right and consist of 5 transforming operators and 3 computing operators. Among the transforming operators, we have, for example, the partition operator that consumes a stream of tuples and produces a materialized tuple buffer that is partitioned by a certain key. We have a sort operator that consumes an already materialized tuple buffer and reorders all partitions by certain ordering constraints. We have a combine operator that joins multiple input streams on a group key and produces a materialized result buffer again. This combine operator is in principle a join, with the additional assumption that the join key only occurs at most once for every single producer, which allows for a more efficient implementation. For the computing operators, we have the hash aggregation, which produces and consumes streams of tuples. We have the ordered aggregation, which consumes a tuple buffer that is at least sorted by a group key and aggregates materialized key ranges without a hash table. And finally, we have the window aggregation, which consumes a materialized buffer and writes the aggregation results back into that buffer. An important detail here is that low-level plan operators integrate seamlessly with traditional operators, since those are effectively only producing and consuming tuple streams. Let's now take a look at how we can derive these low-level plan operators systematically for our example query. First, we need to identify all the different groupings that occur, and we introduce combine operators for all of them. We will try to get rid of combine operators later, but they will ensure that our plan can actually produce all the required aggregates in the end. Next, we collect all the aggregates that are computed for the different groupings. In our example, the topmost combine operator joins the median aggregate and the decomposed average aggregates that depend directly on the input values and the sum that consumes values from the dedicated distinct aggregation. The median aggregate requires the input to be materialized, partitioned by D and ordered by D and A. The non-distinct sum and count aggregates do not require a sorted input and can be piggybacked by this median aggregation. We therefore add a single ordered aggregation operator, indicated by the blue color here, that consumes a materialized buffer and computes the three aggregates at once on sorted key ranges. We then add standalone hash aggregation operators for the distinct sum and the two any aggregates below, since we try to avoid explicit materialization and reordering wherever possible. Next, we add the required transforming operators such as sort and partition for the ordered aggregation and the explicit scan operator on top. We also introduce virtual source and sink nodes to connect the low-level plan operators to the producer and consumer of the former group by operator. The result is a graph that already computes all the necessary aggregates, but might still do unnecessary work. The combine operator here, for example, is redundant since the input and output of this operator are hash aggregations. In a final step, we therefore run optimization passes on this graph. For example, we also try to replace window aggregations with ordered aggregations if the frame boundaries of the window aggregates are unbounded. Or, for sort operators, we select a sorting strategy based on the number of attributes that are actually stored in the buffer, but more on that later. After running these optimizations, we can replace the group by operator and receive this new query plan on the right. As you have seen, the construction of this plan uses graph-based optimization passes instead of an explicit cost model that is commonly used during joint order selection. This might be an interesting topic for future research. Let's now take a look at a few advanced aggregates and how we can compute them with low-level plan operators. Query 0 only contains a variance, a count, and a sum, and can be computed with a single hash aggregation operator. The gist of this query is the fact that the count and sum aggregates are actually redundant, since the variance will internally compute both as well. Query 1 uses grouping sets to compute the sum grouped by multiple keys at once. We evaluate grouping sets efficiently by aggregating specific groupings first, here A, B, and reaggregate the results by key prefixes afterwards. Query 2 contains a sum, a distinct sum, and two percentiles with different ordering constraints. With low-level plan operators, we can first partition and sort the buffer for the first percentile computation, and then reorder the tuples for the second percentile computation. The reordering will be cheaper, of course, since the partitions are already sorted by the partition keys. Query 3 contains a window aggregate and reorders the result for a final order by clause. Here, the window operator already materializes all tuples, so we reorder this buffer instead, followed by a k-way merge. Query 4 contains a median absolute deviation function, which is defined as the median of x minus the median of x. We compose this aggregation function by first computing x minus median x as window aggregate, and then select the median of the reordered key ranges afterwards. Query 5 computes the mean square successive difference by first computing the square difference to the successor using a window operator, and then sum up the key ranges using an ordered aggregation. These example queries underline that low-level plan operators do not add fundamentally new ways to evaluate these complex queries, but instead offer a more streamlined way to reason about composed aggregates. We integrated low-level plan operators into the database Umbra, which uses the push model to generate machine code for SQL queries. I will briefly outline how low-level plan operators can be implemented within code-generating query engines, even though the approach is equally applicable to interpreting systems. This example query here extends the motivational query from before with an additional join predicate. The pseudocode that gets generated using the traditional aggregation logic is shown on the left, the one from the low-level plan operators on the right. We can see that the programs are actually the same, apart from the highlighting, which emphasizes that monolithic aggregation logic might already implement our optimizations today. Yet there are two notable differences when it comes to the code generation itself. First, we no longer generate code for a tree but a graph, which means that operators may need to inline code for more than one consumer. In the example, the join operator produces tuples for the partition operator as well as the hash aggregation operator. Additionally, buffers are now explicitly passed between operators, which will bypass the pipeline-driven code generation of the push model. These buffers are also the primary data structure for low-level plan operators. They store tuples in partition chunk lists and use a row major format to simplify the tuple access through iterator abstractions. These iterator abstractions also allow us to support three different sort modes. We either sort in place, a vector of pointers, or a hybrid mode in between that sorts pointers with extracted key values. We call this hybrid mode a permutation vector, which retains the cache efficiency when sorting large tuples, as long as the ordering key stays, the key size stays reasonably small. The low-level plan operators are simple by design and preserve a high degree of freedom for the actual implementations. In the following, we want to briefly outline how we implemented them in Umbra. The scan operator is trivial, since it only reads a buffer and produces a stream of tuples. The partition operator consumes a stream of tuples and materializes elements into a buffer with multiple hash partitions. The merge operator reads these buffers and merges them with repeated parallel 64-way merges. The sort operator modifies partition buffers in place and reorders the elements using a Morse-driven variant of block quicksort. The combine operator joins multiple tuple streams into a partition buffer and exploits the fact that group keys can occur at most once per input operator. It first materializes all groups of the first input operator and builds a hash table per partition. It then consumes every additional input and merges the attributes into existing groups if there are any. If not, the operator writes them to thread local partitions first and then rehashes the tables between pipelines. The hash aggregation operator implements a two-phase hash aggregation that pre-aggregates an input stream using thread-local fixed-size hash tables that fit into the CPU caches. It flushes collisions on that small tables to local partitions first and merges these partitions across threads afterwards. The ordered aggregation consumes a buffer that is at least sorted by a certain group key and computes aggregates on the individual key ranges. It produces a stream of tuples and may scan a materialized key range multiple times in case the aggregates are nested. And finally, the window operator modifies a materialized buffer in place and computes window aggregates using segment trees if necessary. As you can see, operators like window and ordered aggregation no longer need to take care of the materialization, partitioning, and sorting themselves, and can share intermediate results very easily. In the following, we want to show you that low-level plan operators do not only simplify the development of aggregation operators, but can also evaluate complex aggregates more efficiently. For this evaluation, we chose the main memory database system Hyper as reference, since it also uses code generation and implements very similar aggregation algorithms. We designed a set of 18 queries to demonstrate the advantages of our framework over monolithic aggregation operators. All of the queries aggregate the relation line item of TPCH at scale factor 10. Let's take a closer look at 6 of these queries. The first query computes the three aggregates sum, count, and variance of the attribute extended price grouped by supplier key and has a very similar performance in Hyper. The second query additionally computes the median aggregate, which renders any previous hash aggregations redundant, since we now have to materialize all tuples anyway. The next 3 queries compute multiple percentiles of the attribute extended price and quantity grouped again by the supplier key. Here it is very desirable to compute the percentiles on the same key ranges and reorder the tuples only once for all 4 percentiles. The last query computes the median absolute deviation function, which will be significantly faster when reordering the materialized key ranges by the computed median aggregates. In summary, we observe that Hyper has a very similar performance for single aggregates, but scales worse when more complex aggregates are composed. Please refer to the paper for a more detailed drill down into this table and an additional comparison to TPCH queries. Let's now take a look at low-level plan operators in action. The following 4 plots show the execution traces of 4 different queries. We chose line item at TPCH scale factor 0.5 and 4 threads for the traces to make the individual modules distinguishable. Query 1 sums up line item quantity grouped by grouping sets of supplier key and line number. The plan first groups all tuples by the compose key and then reaggregates the small number of results by the individual keys. Query 2 counts part keys grouped by supplier with and without distinct qualifier. Here, the scan pipeline is now significantly longer compared to the first query, since we are pre-aggregating the non-distinct count and the any aggregates in the input pipeline. Query 3 computes the sum, the variance, and a median of the line item quantity. You can clearly see that the sort pipeline in green color clearly dominates the overall execution time, even though we already sort the tuples in place here, which underlines the importance of fast sort operators for aggregation functions. Query 4 extends query 3 and additionally computes the median absolute deviation function from before. Here the tuples are first partitioned, then sorted for the first median computation, then aggregated using the window operator, and finally reordered again for the ordered aggregation. Especially query 4 underlines the importance of result sharing between the operators, since the cost savings from reordering already sorted key ranges can be significant. Our conclusion is that low-level plan operators can modularize aggregation logic and drive the efficient evaluation of advanced aggregation functions. Thank you very much.